Hello, boys and girls. So I have been thinking about what would be the simplest stochastic process which I can use to explain the power spectrum, or really the autocorrelation function, and its Fourier transform. And this video will be just that. You have it in front of you. It's basically going to be this sort of circle, Markov chain, over which we define a stochastic process, and we compute with a Python script all these quantities, and I've chosen it so in a way that it's not completely trivial, but it's also nice enough so that we can interpret the graphs that you see. So in this case, this will sort of be the end result. I will explain this Markov chain. It has like the capability of setting the size of this ring and setting the probabilities for various movements, and also making it deterministic, so we can compare the completely deterministic case with turning on the stochastic aspect of it. So yeah, the thing I came up with, we want an autocorrelation function and autocovariance function where we actually see some periodic characteristic in it, right? So naturally is some Markov chain, or some set of vertices where the motion is mostly just going in one direction, right? The blue arrows here denote the main motion direction, and we are going to have this situation where you can think of a walker who starts here, and then with very high probability here, it says 91%, it will just move in this direction. So this is the deterministic case, just going in a circle. And then with the other 9%, I let it do some other things. So you could say it freezes in position, or it jumps double forward or backward. In this case, the implementation of this standard Markov chain is such that if it's not moving forward, which is the most likely case at each step, it moves actually one step backwards, and that's how the stochastic aspect comes in. So it's basically, you can think of it like as a walker who tries to go in a circle, but sometimes he's like literally thrown back. Okay, this is sort of the basic setup. The code that I will present has a lot of like debug functionality. I compute a bunch of quantities on the side. I will not to keep the video short. I will not explain all of this. The code is as always in the box linked below, and I will also not explain the plotting code and so on, all the things that you see here. So let's first, before I even explain the code, set the whole thing deterministic and see how the plots look like that. And basically the stochastic version is like the change that comes about if you give it a small chance to actually move in the wrong direction, so to speak. And the two random variables that I will use are those. In the simple case, in the deterministic case, what I will show you in a second, I first use this super simple random variable. But a random variable is a function from the event space into the reals in this case, or in this case even natural numbers. And what this does is it takes the state, which is going to be one of the vertices. They are labeled, in my case, 0, 1, 2, 3, 4, 5, 6, and so on to n. So in this case, if I have the Markov chain with 5 states, it's like 0, 1, 2, 3, 4. And what this thing does is it returns 1 if you are in the starting state, basically the A state in my picture, right? So this was the starting state here, A. And else it returns 0. So this is just for explanation, the first random variable over this graph that we will look at. The other random variable that we will later look at is just taking the square root basically and adding 2. This is just some auxiliary function that I use to have some numerical values over this chain. Okay, I will scroll up. So here I have this flag that I will just set to true to show you what the results look like in this graph if indeed we use simple random variable and the everything deterministic. So here it's the same graph, but the p forward is now 1 or 100%. So this thing will start here and just move in a circle. We have here the I do a simulation and I compute a bunch of averages, but I take the first simulated walk here with 60 steps, right? These things are all part of the configuration here. The walking length is 60. And so here you see this function that has the value 1 at 0, and otherwise the value 0. So right, it's can I show you both? No, I can. The screen is a little bit too small, but you understand. It starts at A, and then in 5 steps goes around the circle, and then another 5 steps, and another 5 steps, and it goes 60 times, 60 steps. And so this is 1, 0, 0, 0, 0, because the random variable at all other states is 0, and then it's 1 again, and so this peaks every 5 steps, right? This is like my random variable. There's no stochastic aspect in it at all. This graph looks like spiky with these triangles, but this is just an artifact from the plotting. So it should be like discrete value 1, and then discrete values 4 zeros, and then 1 again. Okay. And I'm not going into depth explaining the autocorrelation or the autocovariance. Let's start with the autocovariance. I mean, look it up on Wikipedia if you don't know the concept at all. I will show you the code, but it's basically you take the function, in this case, this walk of 60 steps. I choose a lag, let's say a lag of 7, right? And then I look at the function, and the same function shifted by 7 values, right? So x of t times x of t minus 7, and then I multiply these values and see how much they overlap. In this case, if I actually choose the value 7, then I will have for x of 0 the number value 1, and the shifted version we look at x at 7, and it will be 0. So the product at this value for t equals 0 is 0. I hope that makes sense. But maybe the code will help. But it's basically a sort of convolution where you just shift the function against itself and see how much the overlap is. Okay, in this case, if the shift is 0, if the lag is 0, then you have the autocorrelation with itself, which is like 100%. You normalize the thing, and so you have for a lag of 0 the perfect overlap with itself. This will always be the case. Whenever you look at lag 0, the function overlaps with itself 100%. It is clear, okay? But then in this case, if you shift it by 3, for example, here at this place, then you have 0 overlap anymore, right, with the spike function, because the spike function is always like, if you shift the spike function by 3, then whenever the function is 1, the other function, the shifted function, will be 0, and so there's no overlap. So you have no overlap at all, except if you shift it actually by 5. If you take the whole thing and shift it by 5, then again everything overlaps with itself perfectly again, right, because it's a perfect periodic function. And so after a lag of 5, you have an autocorrelation of 5 again, okay, right? So I hope this makes sense for the explanation of the autocorrelation function here, right? This is the autocovariance is you shift it and you look how much overlap is. Autocorrelation just means you normalize it basically to be 1 at the start, and so this looks like this. Okay, and now what we are interested in this video is the Fourier transform of that. So we compute the Fourier transform, we get this thing out. We can then also play further, if we square the Fourier transform, we get the power spectrum and so on and so forth. Since I don't do signal analysis or physics in this video, there's no practical value really, but maybe if I come back to fluctuation dissipation theorem at another point, I actually look more into the power spectrum. In the code, in the Python script. I compute the power spectrum. Here I just plot the Fourier transform directly. Okay, or the absolute value already. So this thing, if you Fourier transform it, looks like this. And why? Well, it has this period of 5, so it should be no surprise that at 1/5, which is 0.2, there's like a nice peak. And then this thing also has like this harmonics. We have a discrete function. We try to approximate it with some nice sine functions. So there's some stuff that is needed to actually make this approximation to this discrete function. So there's some other, I don't want to call it artifacts, but there are some other like things like here at 2 times this main frequency, there's also this peak. These are these harmonics. But the intuition, I hope it makes sense that since the period here is 5, that at 0.2 we see some peak, right? This will also survive if we add a little bit of stochastic aspects later. Okay, and then finally I take the absolute value for a transform, and I just don't plot against the frequency, but 1 over the frequency, i.e. the period length. And so this is maybe nicer to read. There's a log plot here. Here we see at the value 5 we have this peak. So this t equals 5 corresponds to this frequency here of 0.2. This is just another way of plotting the same kind of thing. Okay, so this is the situation where there's nothing stochastic. The thing just goes in a circle around this kind of thing. I will redo it again now, still deterministically, but I just so we have the comparison. I do it for the other random variable, right? So here I add a line setting the random variable to this square function. So this takes the state, right, which is the numbers from 0 to 5, 0 to 4, computes the square root of it and adds 2. So I run this. And so here, not much, well, the period of 5 is still there, as we see best in this plot. But now the function is different. So the function is a lot of positive values. Where this is like, here is like a square, it goes from 2, like basically from 0 to the square root of 4, which is 2 plus 2. So it's always a square root starts, and then after this value it goes down to the start again, because it went around in a circle, right? So this is like 0, 2 plus the square root of 1, which is 3, 2 plus the square root of 2, which is 3.4, blah blah blah. So this is just a square root function, right? And since so much is positive here, even if you compute the autocorrelation, there will be an overlap, and so the autocorrelation here doesn't look too interesting. So what one actually does in the script as well for the non-deterministic part is I will always subtract the mean from the random variable, just so that this plot gives us some more information, some visual information. Okay, that's how this thing looks. And then lastly, I want to mention that here below, if you can read that, we will also compute basically the path that all our simulations take, right? So you have seen, scroll up, to compute the autocovariance empirically as I do here, right? This is not an analytic calculation. I sample stuff and average them. I do here 300 simulations. I could also go up to 2000. It's just a little bit more waiting time. So 300 times let the walker go in a circle. In the deterministic case, this is always the same path. So it goes from A to B to C. You see this here. But now I will turn the randomness on, and then sometimes it will also move back. And here I'm just telling you that in this sprints, I have sort of the animation of how each of these 300 walks look like. Okay, so to turn on the main case, I just turn this underline debug deterministic flag to false. I leave these configs as they are, and I rerun this. And so the first thing, I get the new plot. Let me wait a second. So the first thing I want to point out is that here you can see these simulations where sometimes here, right, with what is my probability? With a 9% chance, it sometimes moves also back. So you know, like 1 out of 9, roughly, steps, it will randomly move in the other direction, and then you see here backward. Then you will see here backwards error, right? So here you see, for example, in the third simulation, it goes forward whole time, except then after like 1, 2, 3, 4. So after like roughly 45 times, it actually moves the first time in the different direction. So this is like controlled with this probability. So for example, if I would here, I will not do it now, but if I go here to 50%, then it's basically pure chaos. Then it's literally a random walker on this bounded circle. I see the best, nicest plots for like values of 91, 93 in this range. Okay, and so it does these runs, mostly moves in the circle, but sometimes also in the other direction. And now the plots look like this. So here you don't see it well here, but there's some backwards errors going in the other direction, which I also draw according to like the opacity of this is given by the probability. It's kind of some small fancy thing, but it's basically invisible. So my point just being, again, sometimes it works now in the other direction. I use again this square function, and here you see already, like in the first step, right, it moves from in this case I start at B, right, because I did not mention this, but to get a nicer average, I have this burn in run. So I actually let it walk for like 300 steps before I even get my final walk. In this way, I don't always start at the same position, but I start however the distribution is. In this case, it's actually a stationary Markov chain distribution. So basically, I randomize where I start from on purpose so that I get a better average with different starting points being taken into account. Randomized starting points being taken into account. And so this thing starts at B, right? This is the second state. My function there is 2 plus the square root of 1, which is value 3. And then I actually go forward, go to 3.4, whatever. And then already actually at the second step, it happens that it moves actually backwards, right? It moves from B to C and then back to B. And you can also see this here in this first run, as I said, from B to C and then back to B, and then it goes on for like another 15 or so steps. So here you see these cuts in this plot. Can I zoom in here now? Okay, I'm too stupid to zoom in here now, but here you see these cuts where the square function does not go up, but sometimes down, and this is because the walker just walks in the wrong direction in this step, right? And so it has to do this walking forward again. Then it exceeds the 4, goes down to this value, and then occasionally it breaks down. Here in this case, for example, at the end here, you see it actually by chance moves down twice. It moves backwards around the circle twice here at around step 58. Okay, and so this random variable you see is not just this periodic function. It's not always square root, but now it's a little bit like obstructed by the walker moving in the wrong direction, and this destroys the auto covariance, right? Because now if you shift, it will not be the perfect overlap, even if you shift by 5, which is the period in the deterministic case, right? And also because here I plot the random variable as I said, but for this autocorrelation plot, I remind you that I actually remove the mean from these samples, meaning the zero line of the random variable that I actually use is here somewhere in the middle, around 3. So you have to think here's the zero line. So this is actually the actual random variable which I use to compute the autocorrelance function. And what you see then here from this effect is that, by definition from the normalization, you have the perfect autocovariance and therefore autocovariance function at 1, at 0. And you still see that there's a little bit of a period here. But because of these walking backwards, because of the randomness which destroys how the curve looks, because of this diffusion basically in this random walk, after 5 steps already, there's no perfect correlation anymore. It's basically removed in this case by half, and just from this 5 it happens to be look like this. And then as longer you wait, the more diffusion sets in, and so eventually this autocorrelation breaks off. Like if you wait for like 25 or a few dozens of steps, then due to randomness, the correlation in the function will be destroyed from all these small breaks that mess with this function, and therefore also the Fourier transform does not look as nice anymore. So still, you still see the period there's a good period of 5, but it does not have the full volume. The Fourier transform is not like just this period of 5 and the harmonics, but it's always like a little bit swam apart by the randomness. Okay, so I hope this explanation sort of makes sense. I'm running out of battery again. I will quickly, 8% I have. I will quickly go through the code, but you might not need much guidance if you want to use it, really. So there's this config, the legs is, how far you go. All these numbers, since it's empirical, affect the quality of the graphs, but I chose values such that the values are not too huge, but don't improve much if I actually make them much bigger. The walk you have seen is also just a few dozen values long. I found like a few hundred of values for simulations is okay. Here is my simple Markov chain implementations. I have previous videos where I have more generic Markov chains with the transition matrix. In this case, it's just the circle, everything is hard-coded, and then these back and forth steps. So num steps you can change, you can choose your probability. Let's say 93 is also a nice number. There's this burn-in, as I said, to randomize the starting state. Below is a function that actually computes the stationary distribution, right? So if I go 300 steps, there's so much random walk, and on this finite number of steps, it's basically completely normalized. Like there's basically a uniform distribution after 300 steps, right? Because you have a lot of steps forward, which basically, these are the standard steps, but then you have basically like a random walk-ish kind of steps in the other direction, and this averages out to being just because the graph is so small to be everywhere equal probabilities. So in this case, if I have 5 vertices after 300 steps, it's basically 1/5 chance of being anywhere. You cannot really guess properly, and so this burn-in produces the stationary distribution, and below I have a function which actually computes the stationary distribution. This is actually, if I run it, it prints this actually, and here you see what you get after 300 steps, the chances of ending up in the different things, and you see it's basically 1/5 everywhere. Okay, so this is the Markov chain. If I initialize it, it is set to randomize the starting state immediately. And then I have the implementation that with the given probability it goes forward, otherwise it goes backwards. And you can, if you really want to, you can extend this. But I have played around a little bit with other motions like freezing or going double back or whatever, and it didn't really change the things from the plot that I wanted to explain. A lot of logs, there's these arrows. Here's this implementation of the stationary distribution computation. It basically does one Markov chain, and then it keeps on randomizing the state, and then plots the dictionary. Here is my two random variables that I used. Okay, and here's the autocovariance implementation. So what I do here, once I have a walk, which is basically a sequence of vertices on the Markov chain, I compute the random variable values. Right? This is the stochastic process, the x, capital X, or here in Python, the x's. I compute the mean because I told you I will subtract the mean. And the here you see the implementation of the autocovariances. So I take the values and I shift them. This is shifted or truncated from the side, and then I compute the inner product. This is similar to a convolution, and this is sort of like an energy quantity, right? I mean, vaguely you can think of it like kinetic energy v squared, but this is like just vague correspondence. And then I have computed the autocovariance for this walk, and this